Okay, guys, so let's move to the front up part of the class. As you notice, we are recording, so be aware that if you have any interaction, then it will be recorded. Not a big deal, just letting you know. So, starting from this lecture, we're going to be sharing also the author notes over the Slack channel. So let me know if you find the author notes also to be useful. And yeah, that's all. So just a second, let me check that the author is indeed in the call. My author is here. Okay, very good. So as always, we thank the people at Harvard for the data for the slides. We always use the CS109 set of slides because it's a very good course. There is no point in producing the same notes multiple times. So for today, we want to discuss a little bit the different type of data and the different format of the data, how to select appropriate data, how to be aware of the biases in the data, and how to be able to refine our question based on the data is available to us. So I think that through the challenge for this week, you had to deal with your first taste of what big data means. Big data means millions and millions of entries, very complex formats, possible very structured information, and the issues that you have, right? The issues is missing data, unreliable data, changes of format in the data. So there is a lot to be discussed in terms of data formats. We just go through a brief presentation now, and then we move on with our life, having a certain awareness of this. So let's see, the agenda is what is data, what are different aspects of the data, how to ask precise question, and how to parse expression. So let's start from the question of what is data, right? So we can have different definitions of what data is, and usually different communities will have a different definition of what data is, right? So for example, you can define data as a factual information, such that a measurement or a statistic, which is used as a basis for reasoning, discussion, and calculation. Or this would be more maybe a statistician definition of data. A person with a background in computer science, he will say that data is information in digital form that can be transmitted and processed, right? So it is clear that there is an aspect of digitalization of data when we discussed about big data that cannot be ignored, right? A human person, human individual has finite capabilities of reading manuscript, flipping through sheepskins, reading through stone tablets, right? So the ability of having an automated processing of the information, it's of course very important to our definition of data. And the definition 3, information output by a sensing device and organ that includes both useful and irrelevant or redundant information and must be processed to be meaningful. So this definition is maybe what an engineer will see, right? So an engineer will say that data it comes from a source of information, and this source of information is prone to error, is affected by failures, and produces data which is relevant only after processing. Okay, so when we discuss about data, remember that we can have many definitions of data, all reflecting some important aspect of what we wish to discuss when we talk about big data and data processing. Okay. So let's go through the first definition of data, which is that of factual information. So the scenarios in which you'll be collecting data, for example, would be a measure from a thermometer, right? It gives a measurement for every year, the counts of a certain person that does a specific type of birds, the tweets for representation, or a readout of some mysterious sense on the purchase on the local sales. And we see that if you go through this different example, so if you are counting, for example, birds, there are some inaccurate data because the counter could be affected by some mistakes, and there could be missing data, right? There could be a certain day in the year in which the count is not performed. tweets from a politician have the bias of not being 100% factually true. So it would be really hard to extract factual information from the tweets of a person with a specific agenda. And even if we take a mysterious sensor that let us know about the purchase on the local yard sale, it's clear that we do not know anything about how the measure has been taken, but we can still treat it as digital information for us um, to process. Okay, so what is data? Another view is this. So we can see a sort of a hierarchical definition of data. So datum is a single piece of information, can be treated as an observation. Right? Data is the plural form of this, and it was constitute a set of observation, and then a data set is an homogeneous collection of data. Okay, so if we had in more of a computer science view of this, we will say that datum is some single feature that is observed. Data is a row in your data set, so it's a collection of features, and the data set is an homogeneous collection of data. Right? So we have multiple observations on a certain phenomenon, which is compiled in a way to be homogeneous. Okay, a little joke. You can read through yourself. So everything can be data. As you become more involved in data science, you will see that the difficult part of data is the data collection, right? So always when you want to produce some meaningful data, the aspect of data collection is very critical, right? For example, let's think about the first case. The first case would be the thermometer, and you can understand what effort is involved into collecting data from the thermometer, right? So you can imagine that maybe you want to know the temperature. What was the example before? We are looking for a thermometer, let's say, on a person for every hour of every year. So what you can do is that you can digitalize the thermometer reading, connect it to a data set, and move on from there. If you're counting birds, actually, you need somebody to go out with binoculars and try to observe the birds. So this is a much more involved aspect that cannot be easily digitalized. And so on and so forth with our examples. Okay. So you in data science is a relatively new approach to science, which relies on the availability of vast amount of data. And usually the people in data science like to think about the generation of data in this type of pipeline. First, you have to start with an interesting question. Okay, so always in science, the first thing that we wish to do is to ask questions, right? If we do not ask questions, all our operations, all our efforts are meaningless, right? So first we have to be very sure about the goal that we are trying to achieve. And once we are very sure about this aspect, then we can go and collect the data. Okay? It happens often that you want to have, there is a phenomena that you observe and you want to collect the data, but if you don't have the precise understanding of the questions that you want to ask, then this aspect of collecting the data is just a waste of time. So often people think about the example in the medical studies, right? So let's say that you want to do a medical study and you want to know the effect of a certain drug. It is people, literally spend years trying to design a set of questions that you want to ask with this type of data collection, meaning that if you decide to see the correlation between certain medication and weight, then you have to have a very precise pipeline with which to measure weight, choose your population in a way which is meaningful. So the process of ideation of the data collection is really important. Okay, so the conceptual part is asking the question, then the effort goes into collecting the data, and once you have collected the data, you have to explore the data. And this is what you guys did in the challenge 0 with the 1 million songs data set. You have to figure out how to visualize the data, because we only have 2 eyes and we live in a 2-dimensional world, so it's very hard usually for human to process this vast amount of data. You have to figure out some data summarization, some data visualization techniques that can guarantee to you that the data that you have is high quality data. Then you have to model the data. Okay, this is the discussion, the topic of the course. You are given a large amount of data and you want to produce a model. What is the role of the model? The role of the model is to identify these input response type of relationship. You want to predict what will be your observation under certain initial conditions, for example. And so the creation of the model is again a very, very crucial part, because basically the model has the ability to summarize the relationship between features that you have observed in the data during your data exploration phase. And then you want to communicate and visualize the results. And this aspect is also very, very important because most of the times when you produce these results, you have some downstream application of these tasks. Okay, so let's say that you have built the perfect model to predict a baby's height from so let's say some data collected in the first week. So of course, most of the times it's not like predicting the baby's weight is not so important in itself, but it's important because it enables some downstream processing. So, for example, it allows for a doctor to take decision, for a family to take decision, for a school district to take decisions, and so being able to communicate your insight on this process, it's also very, very important, and it's something that generally engineers and computer scientists are not particularly good at. So it's also something to keep in mind. Okay, very good. And what we want to comment here is that there is always a sort of cycle here. You cannot imagine that you're going to go through the process of ideation of these data science efforts and be always sure that you can go from point A to point B. Often you have to loop around between getting the data, exploring the data, asking what is the question that we can answer with the data that we have, going back, collecting more data. So of course, while it would be nice that we can ideate the full process from top to bottom, of course there are a lot of iterations to be done on this. So computer science is mostly concerned with computational model and related aspects. And our focus is what is computable, how can you efficiently compute something, how can you store the data, and so on and so forth. But of course, it's also our duty to be able to communicate the results of our finding and being able to design experiments. Okay. So let's now discuss about different aspects of data. So we want the data that can answer our question and is preferably easy to work with. So data come in all shapes and sizes though. So for example, what is the data necessary to answer a certain question, how difficult it is to analyze the data set, is the source of the data authoritative, is it comprehensive, is data comprehensive or is it sample data, what are the biases that is present in the data, and so on and so forth. And then so we can explore some of this question next. Okay, so for example, how difficult it is to analyze the data set, how comprehensive is the data, and what are the biases. So this plot is really nice because it really tells a story which is really the story of the past years of machine learning, right? So you can imagine a plot where we have two axes. On the x-axis, we have how easy it is for people to work with, and on the y-axis, it is how easy it is for computer to work with. So the best data that you have will be, for example, a table. The table is very easy to work for a person because we can visually inspect the data set. So in this case, we have a data set of people, their age and their height, very easy for us to analyze. But also, it's also very easy for computers to analyze because it's just data entries, right? So we will have just some digits. We can represent the digits with floating point 16 and whatever, we can move on. Then we can move on the axis of what is the hardest things for people to deal with and what is easy for computers to deal with. Of course, if you think about a QR code, you cannot read the menu at the restaurant by just looking at the QR code. Of course, you need your phone to do so because humans cannot work with QR codes. And generally, right, there was an understanding of what type of things are hard for computers to work with. So generally, people would have said that if you're provided a video, for example, a movie, you should know which movie is this. It's a great movie. But if you're given a movie, this movie is very hard for computers to work with because there is a lot of visual information which is hard for computers. The size of the computer representation of this movie is gigantic. So, for example, if you provide a movie in 8K to a computer, it will be multiple gigabytes of data. It will be very hard for the computer to parse the video frame by frame and understanding what is the semantic context of the movie, the choice of color, the choice of lighting is something that would be difficult for a computer. And so this is a difficult format for the computer. And then you can move what is easy for people and hard for computers. For example, you will also have speech or let's say a video game playing, because it's clear that that these are complex formats that can be represented in a computer format, but of course they are designed for human consumption rather than for machine consumption. But the point that I want to make here is that, of course, the breach of machine learning in the last years has been the ability to actually understand very well the information which was designed for humans, right? Notably NLP, natural language processing, and video, right? So they've been the latest data format that computers have been able to understand as well as humans. And for example, if you talk about video information, then you can think about Sora. It's going to be released soon, and we all want to know what Sora is capable of. And NLP, you can think about your ChatGPT, how well it understands human language, right? So this plot is a plot which is relative maybe to the classical view of data without taking into account these advanced computational models that are available to us. And then another consideration is whether the data is comprehensive or not. Okay? So, for example, if you think about these sources of information, New York Times, Twitter, and Congress.gov. So, for example, you have access to the data observation that exists, which is usually a lot, and the collect and digitalize information. It's produced by a certain institution, right? So if you think about the New York Times, there is a lot of effort to cover all sorts of relevant information regarding an article. You don't expect that the New York Times to make some factual mistake in the reporting of the data. But of course, when you look at Twitter, then Twitter is just a mess, right? There is no control of the information which is used on Twitter. Another consideration is whether the data is extensive or it's sample data. So often you don't have the ability to explore all the data sets. So for example, let's consider the IMDb movie dataset. So this is a classical dataset in which they will have the name of the users, and you will have the ranking that a certain user give to a certain movie. Of course, it would be nice if we had access to a table that tells us exactly for each user in the galaxy what was the ranking that they provided of a certain movie. But of course, this data is not produced, right? Most people don't watch most movies, and so what you actually observe in practice is that you have sample data. You have some access to the score of a certain person, of a certain data, and you are asked to predict, for example, what another person will think of a movie. And this goes into the recommendation systems, right? The recommendation system indeed is a model that takes sample data and tries to provide samples of another data. So you look at the data that you have and you try to predict what would be the scoring of a person to a certain movie if they watch it. Okay. Then another very important topic is that of biases, right? So what is the bias that is present in data? And this is something that it's impossible to predict, okay? So usually you do a data collection, you do all your experiments, and then you figure out maybe years later what was the bias that is present in the data, and you were unable to predict at the time of design of the experiment. For example, omission. If you think, for example, some people don't want to answer some question. What is a good example? A good example would be, have you ever cheated on your wife, right? So a lot of people, even if the collection of the data is private, and so on and so forth, most people will not admit that they cheated on their wife. So they will omit the information, Or if you ask a person if they ate junk food in the last week, most of the people will say that they didn't because they don't want to admit to themselves that they ate junk food, right? So you might do a very comprehensive study on the dietary habits of people and only figure out years later that people usually lie when it comes to dietary information. And this is something that it's well known in the literature, right? So it's a bias which is well known in, for example, in the nutritional literature, that people always underreport their use of junk food. Source selection. So you might want to include sources. Sometimes you have to include sources that are more or less authoritative on, let's say, the two different sides of an argument. Again, here a classical example is that a lot of, for example, psychological or sociological tests are administered on campuses. On campuses, most people are between 20 and 30, and they come from a certain background that allows them to go to university instead of going to work a certain job to earn money. So there is always bias in this type of test on the fact that the participants to the data collection are not randomly selected across the population. Then there is something which is more malicious from the point of view of the test designer, which is story selection. Even if we are not aware of it, we usually tend to prefer data that agrees ahead of time with the story that we're trying to tell. So we are writing a paper again on how bad nutrition is for people, and so we try to find sources of data that reinforces the view that we want to write a paper about, and we might not be aware of it, but of course this is a bias that we have. And placement. Okay, so this is another very important topic, right? So you might argue that the science that gets made is not the science which is coming from the sky, inspired by pure intellectual pursuit. But of course, everybody's trying to get grants, so everybody wants to do research on topics that are of relevance, and everybody wants to tell a new story on the topic of relevance. So when we do data collection, we are always trying to obtain attention, to gather money. And so the type of experiments that we do, we are always biased toward this type of thinking. Okay, very good. Yeah, so more on the maybe news type collection or argument collection. So when you collect data, you should take into account the both sides of an argument that can be made, and then you have to prevent spin, right? So you have to prevent changing the interpretation of the data to fit your own agenda. So remember that biases are very hard to discover. They are most of the time unintentional, right? If they were intentional biases, then people would be barred, or they would be easily criticized. So the hardest biases to realize are the unintentional one. And yeah, it's always a struggle to minimize the biases in data collection. So just an example here. For example, you always see these polls that they predict, let's say, who will win a certain election, who will vote for what. And in the US, the agency that does this is Gallup polls. So you can look a little bit into data collection for this type of a political prediction, election prediction, and you will see how it's done. So usually there is a data set of people that answer phone calls, and they call, let's say, 500 people among all the people that responded from phone calls, and then they try to select landlines based on maybe some racial background. They try to call people that are in a certain coverage of states, and then they try to weight the data that they collect by the demographic general population. So, for example, classically, most people that answer to these polls are older people. There are very few people that answer to phone calls these days. Most people that have time to answer maybe are of a certain ethnicity. There are fewer ethnicities that are willing to answer a phone call from an unknown number. And so even if you collect the data, being aware of the biases in data collection means that you have to manipulate the data a lot after it is being collected to account for these biases, to compensate for the biases that you have in the data collection. And of course, by the time that you do all this compensation for the data that you have collected, trying to correct all possible biases, you have transformed the data to a point in which it would be impossible for you to not recognize that this type of correction is itself introducing some other bias by the design of the correction. Okay, so this one we already talked about. The IMDb movie ratings. This is a very famous data set. I think it was maybe 15 years ago when there was this big IMDb movie dataset challenge. So they gave $1 million to a certain group that was able to produce reliable prediction for the rating of the movie. Okay, so they had the problem that they wanted to build a recommender system. They wanted to recommend people to watch a certain type of movies. But of course, this is and they had a very large data of movie ratings. But of course, there was the beginning of data science as we know it now, and then this problem of predicting system recommendation was not as well understood as it is now. And so people competed. Somebody won the money. It doesn't matter. What happens after the competition is also very interesting because people went back to the type of data that was released and they did some data exploration on this data. And for example, they were able to de-anonymize a lot of users because they figured out that the information that was revealed by this could be linked to some preferences, and the preferences could be retrieved from, for example, some groups that you belong to on Facebook. So they were able to de-anonymize a lot of people. And among the data exploration that they did was to see the bias in movie ratings and sex. So basically, usually female users will try to rate a certain type of movies, and they will have a certain review for the movie, while guys, they will rate another set of movies, and so on and so forth. So one example here is that among the people that they rated Sex and the City. So this is a movie from Sex and the City was a TV show maybe from 15 years ago about this group of friends that live in New York. Don't ask me too much about it. Okay, so most of the ratings were coming from women. So there was a prevalence of women ratings, and the women gave an average rate of 8.1, while the men gave a rating of 5.8. Of course, there is a story to be told in the data. There is a bias that connects gender and rating, and this is something that you have to be aware of when you design a recommender system, for example, right? Because of course the rating will change. And yeah, so this website is something that you guys should check out. 538. I also read the book of the guy that has this website. It's usually very insightful, and they provide a nice statistical exploration of data. So here there is the share of ratings 1 out of 10 of the movies, and here there is the imbalance, right, between male and female, and you see that the movies that most women ranked are ranked higher by female and are ranked very low by male, and then you move toward the spectrum, and these are most of the movies that are ranked by guys, and guys give a very high ranking. So you see this. The story in the data, right? You see that whether you are a male and a female determines the ranking of the movies, introduces a bias in the ranking of the movies. And then, yeah, there is the average difference between the ranking of a guy gave to a movie targeted to females and vice versa. So very interesting data in the movies. Then there is an example for Yelp. We will not go through this. So this is evidence that bias exists. So another type of description of data that we can have is the format of the data. So usually computers are very good at manipulating numbers, manipulating photos and videos, and audio is usually more computationally intensive for computers. And so usually computers are good at working with structured data, such as spreadsheet and data files and so on. Whether unstructured data like NLP and images are just harder for the computers to parse. So, for example, if you had to try to feed this Lewis Carroll story to a computer, then you will try to, for example, convert this object in a CSV file, try to separate the tab in a certain way, give a certain index to a certain element in the vocabulary, and then try to train an NLP to use it. But of course, this is much harder than just reading tables from a column and processing things. So I guess some of you were familiar with the XML format for datasets, and then you have seen these other formats. So JSON, I think you've seen it, and pandas, and yeah. So some consideration here about the data formats, and then it's important to reevaluate the questions that you ask as data comes in. For example, it's crucial for questions or inquiries to have a precise and defined terms. So, for example, let's say that we want to say whether voting is an all-time high or not, and we want to prove whether this is right or wrong. Of course, we have to specialize. So whether is this in a certain specific country or worldwide, what type of voting? Voting can be presidential races, local elections, federal elections, so on. What type of metric? So whether percentage of the population, whether you want to account also different aspect of the population, and then what is the time scale, right? Because people have been voting only for a relatively short amount of time, let's say maybe 100 years top. Less because there were no women voting 100 years ago. So of course, what it means to vote changes through time, and all-time high uh, changes the meaning as time passes by. And then yeah, so as the question becomes more high level, then the type of data that we have to collect to be able to give a meaningful answer also increases. Okay, very good. So in general, more specific questions provide more meaningful results, and you have to be aware of biases as much as you can, and always questioning the results and the conclusion that you're trying to draw from the data, especially against your own understanding and your own biases and your own story to tell. And yeah, so just the last one is about parsing regular expression. I think this part here, it's okay for you to go through yourself. So just some examples here on how to use Panda and how to, for example, create a data set from Twitter by extracting the age, the different tags from Twitter. Yeah. Okay, very good. So I'll let you go through this as an example for yourselves, and I think it's all okay for now. So I'll give you like 5 minutes for a question maybe, and then we move to the next set of slides. As I said, today is still a very light class, so no worries. So next we go to something a little bit more interesting and less less high level. Okay. Any questions from the audience?
Yes. Could you explain again if how they found out the names of the people from their film ratings, from the movie ratings?
Yeah, so also there is a lot of sun in my room. Okay, so basically at that time, there was a very nice API for people to download for example, the groups in which you belonged on Facebook. Okay, and some people, they had the same username on IMDb and the username on Facebook, right? So don't ask me, like if you, let's say my IMDb username was Rini_Stefano, then it wouldn't be possible for you to find me on Facebook. So they first created the data set with the clear users, in which they could link the Facebook account to the IMDb account, and then they created this data set where they had the prediction of the groups that they belong to, based on the Facebook profile, and then they linked this to the movies. So let's say that or is an example which is not too racist, but anyway, so let's say that you watch a lot of movies about animals, and then you belong to some bird watching. Okay, so let's say that there is a movie about birds, and then you belong. They figured out that the clear user, the user they could connect, they also belong to some bird watching association. Then you could go through the data set and figure out that the some user of which you couldn't associate to a Facebook user watched the same movie and belong to the same group, and then they correlated them together. And then they repeated this for larger and larger, groups and set of users and features. So, for example, if somebody at a political association that was known, they also tried to link the political association, and it was a big understanding for the community that the privacy leakage that comes from online data is just gigantic, right? Because they could de-anonymize a bunch of users just from from some side information that Facebook was willingly sharing with people, and yeah, and there were no concern about the privacy leakage. Yeah. Was the question clear?
Yes, thank you.
Yeah, so not talking about this, right? So you remember when Trump was elected the first time, maybe 5 or 6 years ago, Facebook was fined by the UK government, because basically when you give some information to Facebook, that they can then use it for target advertisement. So if you're trying to sell tables and there's a person that belongs to some woodworking group, you can do the target advertisement. But Facebook let I think the Trump campaign use the target advertising for political advertisement, and and they were targeting people that belong to some conspiracy theory group, and so it was a big. They were fined. They was fined a lot, like a couple of $1 billion in the UK, because they allowed for targeted political advertisement using information that should have been private, right? Because there's always the idea that your activity on Facebook is private, but actually it's not. Okay, very good. So now we can move to the presentation of k-NN. You guys should be able to see this. Okay, so k-NN, again, all the credits to our friends at Harvard. So let's talk about statistical modeling. What is the k-NN? Model fitness and comparison of two models. And then we're going to discuss a little bit linear models. So we're going to go 20 minutes on this, and then we should be done for the day. Okay. So we discussed data so far, and we said that after we collect the data, what we have to do is that we have to create a model. So k-NN is the stupidest way for us to create a model. And the purpose of this model is to create a prediction, right? So we want to have some algorithm, some mathematical procedure that is able to produce some prediction given some input features, okay? So let's say that we are trying to predict the number of views of a YouTube video based on the length, the date when it was posted, and then the previous number of views, and so on and so forth. And you can imagine the same thing for the Netflix, right? So you're trying to come up with a prediction for the performance of a certain Netflix documentary or whatever, and you want to do it based on the previous ranking provided by other people. So this topic is generally very, very difficult to address because you have a number of variables. So now, for the time being, let's assume that we fix to this very simple example with 4 features, and the features that we have are the advertising data. So let's say that you have an advertising company. You can decide to allocate a certain budget for TV commercial, radio commercial, newspaper commercial, and as a result of this advertising, you see a certain amount of ratings. So you release a product. When you release a product, you decide the budget of advertisement. You see a certain number of sales. You try to abstract away what was the product itself, and you just want to see what is the result of the advertisement on the sales. Okay, of course, this is a very dated data set because nobody uses any of these technologies now, right? So TV, radio, newspaper, they're all dead to us as people of the digital age. But we can be a little bit nostalgic and see what was the what was the discussion in 2013, okay, when this data set was collected. Okay, so it's clear what we want to do. We are releasing a new product. We want to decide the budget on these 3 different advertising routes in order to maximize sales. So our response variable will be what we want to predict are the sales, and what we want to design is the budget. And this is because the following asymmetries exist. Some of the variables are easy to measure, are easy to control, and other parts of the variables are harder to measure and harder to control. For in our case, if you go to this example, it's clear that we can take an action on selecting the budget, and we can have an historical record of what was the result of the budget. So these features are very hard. The first 3 columns are very easy for us to collect. The sale ones, we can also do it, meaning that after we have sold all these goods, we wait for 5 or 6 years and we see what was the total sales of the objects. What is hard, right? Of course, is to decide what are the sales at the moment of making a budget. right? So we want to make a budget, and we want to predict what would be the number that we would have collected 10 years later after we have sold all the goods that we are trying to market. So there is a natural asymmetry between the variables that are easy to control, easily to measure, and the ones that are hard to control. Okay. So usually the ones that are easy to control are the ones that we put in our features, and the ones that are hard to control are the ones that we want to predict. And so we put it in the predictor. So it's clear that the sale could be our response variables, and we want to use the observation of the past budgets in order to predict what will be the sales. Very good. So usually we use X for the features and Y for the response, as you can imagine. And usually we use N for the number of observations in the data set. So this is the historical record of performance. And we use P for the number of features. And in the following, the response is going to be just a scalar. So usually we're going to have this number, right? N and P number of elements in the data set, P the number of predictions, and the response is going to be a simple scalar, just for the moment being. So we have in total P plus 1 variables, and we have n observation of these P plus 1 variables, and we would like to predict the outcome or the response, which is Y, from the features or the predictor, which are the one from 1 to P. Okay? So usually with Xij, we indicate the ith observation and the jth feature. So the Xij will be the row I of your data set, and the column J will give you the value of this specific feature, or this specific data. Okay, good. So in general, we have to assume what is the relationship between the input and the response. Okay, so this is also a very long discussion to be had, but usually what you say is that you assume that the Y is equal to a certain f of x plus epsilon. Epsilon will be your noise, a certain set of random amount, random distortion, random effects on your response variable, and then you have an f, which you assume to be a deterministic function. So you assume that your observation that you have is equal to a deterministic function of your inputs plus some noise. Crucially, you assume that the noise is independent from the input. So you assume that for whatever input variable you have, the behavior of the noise will always be the same. Of course, this is not the case. This is a simplifying assumption because we need to live a life and come up with practical algorithms, and consider the influence on the input on the noise is generally too hard for the time being. And so we just want to have this independent noise, which simplifies all our approaches for the time being. So we will call this a statistical model, meaning that we have a statistical framework for this. So for if we put the same input, we're going to see a distribution of the response variable, which is determined by the randomness of the noise, and we can then try to design an algorithm which approximates the f. So this deterministic behavior, which is the one that we can sort of nail down with our model, and we are going to call this estimate f hat. Very good. So then for the different classes of fs that we choose, we could choose f hat to be all the linear functions or the polynomials or whatever function you can come up. You can try to find the element among the estimates that you want to predict, which is closer to the true model. So let's add here a little bit of a plot. So you see here the budget on TV advertisement on the left, on the x-axis. It goes between 1 and 300, and then the sales that again goes between 0 and $25,000, whatever it is. It's clear that there is a certain trend in the data, which is if you don't spend money, then you don't sell goods because people don't know that they are selling them. And then there seems to be maybe some sort of linear relationship between the budget and the sales in the regime between 120 and 300 PV budget. Okay, so in this case, we will say that the response is Y, the predictor is X, and what we are trying to do is to create a statistical model that predicts the certain Y value for a certain X budget. Okay, so this is what you will call inference, right? So you have a data set that tells you the past experience that you have from the data, and then what you want to do is that you want to say, okay, now I want to set a new budget and I want to predict what are the sales. So what is the simplest thing that we can do, right? So again, let's simplify things just on TV budget and sales. We're going to be in 2 dimensions, so we can plot some nice plots. We can worry about the multi-dimensional later. So of course, something that we can do is just to say, well, let's say that now I want to fix my TV budget here. What should I expect as my sales? So this corresponds to a point in the x-axis, and you want to find the corresponding point on the y-axis. Okay. And if you change the type of budget, you would like to see what is the corresponding sales, and you would like to change, let's say that you would like to choose a sweet spot in which to do this prediction. Okay, so what is the simplest thing to do? Well, the simplest idea is that you will predict as your response the average of the responses that are next to you. Okay, so this is very simple. You take a point, you choose the points that are next to it, and you predict as the outcome the average of the points, and you call this the predicted value, and you choose your y hat to be simply the mean of the values. So if you're here, you will predict. You will look at the difference at the points next to you, and you will predict your x to be the mean of all the other points. This is not. This is very clear. And if we do this for all x's, we can limit ourselves to, let's say, taking an average. So you see that here what we're doing is that we are looking at the points which is closest to us, and we are choosing as the, sorry, just a second. So the first idea is to just take the mean of all the points in the data set, but this idea is not great. So what you can do instead is that we can just look at the point which is closest to you, right? And you can predict that the sales that you have are the correspond to the sales which is closer to you. So let's say that we take this point on the x-axis, we call it xq. We look to all the other budgets close to us, and we predict the same sales as the closest point to us. Okay, sorry, I got confused a second. Then we figure out that this xp yp is the closest one to the budget that we have. So we will predict that the sales that we have, if we choose a budget xq, is going to be yp. Why? Because yp is the feature, is the response closest to the feature in the dataset to us. Right? So we go through the dataset. We want to find the closest xp to our xq, and then we predict the same response as the closest feature to us. And if we do this for our response, then we obtain this. Okay, you see that here it's very intuitive, right? So you have these flat areas, right, that corresponds to the same prediction as the data point, which is with the x. Okay, so basically how you obtain this flat area is like this. You have this point here, you have this point there. You find the midpoint. So left to the midpoint, you're going to have the left prediction as being the prediction to your input, and for the right to the midpoint, you have the next prediction in the line. Very good. So you see that now we are using the dataset to sort of pin these regions in which the prediction remains the same prediction as the closest data point that we have. So far, so good. But then we realize a little bit that we are being a little bit too overconfident, right? Because we are just looking at the closest point. So maybe we can have a better behavior of our prediction if instead of taking 1 point, we take 2 points. Okay, now let's say that we go through our data set again, and we look to the 2 closest point to our xq, and we obtain 2 responses. Let's say yq1 and yq2, and what we declare is the average between the responses of the points that are close to us. Okay. And we can repeat this behavior for all possible number of neighbors. So we can go from 1 neighbors, 2 neighbors, 3 neighbors, 4 neighbors, and then take the average. And this is what we will obtain. So for k equal to 1, right, we just produce the prediction, which is the closest one to the current value that we have. So you notice that this curve has a lot of jumps. Why? Because the prediction that we have changes completely when we move beyond the median of 2 different points. We can try to do a little bit better with k equal to 3. So for each point on the x-axis, we look for the 3 closest points in the dataset, and we do a prediction, which is the average of the response of these 3 points. Okay, and here I get this dash dotted line. So you see that this dash dotted line, now it has a smoother curve, because I'm not changing value so drastically, right? I'm changing value whenever the neighborhood changes, right? So I'm averaging across more and more points when I move along the curve, so it's unlikely to have very high jumps. And then I can go to the extreme case in which I use my whole data set as the neighborhood. So I fix my k equal to 8. So for each point, I take the average for the data set, and I get a purely flat line because this is the average of the data set. Okay, so you see that you can manipulate the behavior of the predictor by changing the k. So the smaller number of k gives you the fastest response to a change, but also the rapidest one. And as k increases, the prediction becomes smoother and smoother and smoother until k is equal to the dataset size, in which case you have a constant, which is the average of the dataset. Okay. So of course, things are not interesting when you only have 8 points. Let's say that we take the whole data set. Let's say that we have a few hundred points in the data set. You see here the axis corresponds to the points in the data set. You see how they jump around. You see the k equal to 1 changes very rapidly because it's changing prediction whenever the closest neighbor changes. Then you set k equal to 10, you have a smoother curve, and then you set k equal to 70, and you get this flat behavior plus a rise plus a flat behavior. And then you can try to reason over this curves that you obtain, because again, you have the availability of having multiple predictors. Remember that your job is to predict the budget of the model, the budget of a certain sales. And in order to do this, you have created a model, and the model that you have created has a parameter which is your k, and your k tells you how you should obtain the prediction of your sales from the dataset that you have given. So if you take different values of k, you're going to have different predictions. And now your job as an algorithm designer is to decide what is the most meaningful value of k that will give you the best prediction. We will spend quite some time in understanding what does it mean best prediction, but let's just try to read what is the story from this figure and how it's meaningful to us. Okay, so if you choose k equal to 1, it's clear that this is not desirable, right? Because basically, if we move over a small amount and we cross the median on our budget, then the behavior of the function changes so drastically, which is undesirable. You're telling me that if I spend $23.5 $1,000 on that TV advertisement, then I will get a sales of, let's say, $10,000. And if I move of $100 more, then the prediction of my sales is going to increase of tens of thousands of dollars. Of course, this is not a desirable model, because you can go to if you go to your client and you tell them, oh, if you increase the sales by $100, then your earnings are going to increase of millions of dollars. Of course, this is not something that they will believe, right? There is a certain smooth behavior, right, between the input and the response, which one will expect from a good model, which is not present in this. Okay, so then you try to do a better job, and you increase your k of 10, and now you see a certain behavior which is intuitive, right? Because you see that for small budget, you have almost a linear increase of your revenue with your budget, which is sort of intuitive, right? The more you advertise, the more you sell, and the relationship between the two is a linear relationship. But then it seems that there is some saturation, right? For higher budgets, it seems that there is a saturation, which is actually what you expect to see, right? People have a certain disposable outcome, and even if you see the advertisement of your product on every wall of their house or their working place, they're not going to buy the good if they don't need it, if they don't have the money, and so on and so forth. And so this seems to be a good model. If you get k equal to 70, then you have a model that says, oh, it doesn't matter if you spend thousands of dollars or hundreds of thousands of dollars, then your response is always going to be 1. It doesn't matter if you spend $200,000 or $300,000, your outcome is going to be the same. So here it's also an undesirable model, because if you go to your client and you tell them, oh, it doesn't matter that you spend X or 2X, your response is going to be the same. Of course, this is not something that your client is going to like, because you don't expect this type of unresponsiveness of the system, right? So you see that now you have designed an algorithm, you have a key in your hands that tells you how to control the behavior of the algorithm, and then it's a responsibility as an algorithm designer to produce the best prediction, even a family of models which is controlled by the parameter k. Very good. So this method is what we call the k-nearest neighborhood. This is the most intuitive way to predict a response variable given the data set. And the idea is that you look at your k-neighbors and you decide that your response has been the average of your k-neighbors. This is importantly a non-parametric learning algorithm. So there is a lot to be said about non-parametric stuff, but the idea is that it does not make any assumption on the underlying data. Okay, so as you see, the models that we're going to see later, they will assume that the data, for example, has a linear behavior or as an exponential behavior. It assumes some underlying trend in the data, which is not assuming the k-NN. So why it is, say, not very complex as an algorithm, it is important because it doesn't have any assumption on the distribution of the data. And one thing is that in this case, we are producing a response which is a continuous variable. This algorithm is also able to predict categorical variables, so responses y that are in a certain category. We're going to see this later, and can be used for classification. This is another problem that we're going to see later. And the k-nearest neighbor is also very intuitive as an algorithm from this point of view. Let's say that you are a doctor. You have a historical patient that you've seen that came in with a different set of symptoms, and you predicted the illness that they have from the symptoms that you observe. It's clear that when a symptom comes in, what you do as a doctor is that you go back to your experience and you predict the illness of the patient by looking at the closest symptoms that you've seen in your previous patients. Okay, so it's a very human way of making prediction, and the algorithm is stated simply: somebody gives you a data set of features and predictors and predictions, x and y's. You have n of those. Or somebody then gives you a new observation, which you say it's the x and y pair. What do? Is that you go in your data set and you find the closest variables in the data set to your input feature, and you do a prediction, which is the average of the response of the other observation that you have. Okay. So this description is deceptively simple, meaning that the way that you calculate the distance between your input feature and the elements in the dataset could be very complicated. So, for example, let's go back to the case of the doctor, right? Let's say that one of your input feature is some X-ray. Okay, so you have an X-ray of the bone of a person. It's clear that the way in which you take the distance between the X-ray of your current patient and the X-ray of your previous patient cannot be a simple Euclidean distance, right? You have to decide that you need to do some processing, you have to do some detect some edges, and then take a distance between the edges of the bones after you have aligned some other edges. So even if the algorithm presented so far is simple in that the distance calculation is simple, then in reality things are could be much more complicated in evaluating the distance. And also this average operation, right? So this average operation is simple here because again, it's an average in the Euclidean sense. So we just take the sum of the points and we take the sort of the center of mass of these y responses, the average vector of these responses. Of course, this operation of average can be infinitely complicated if, for example, your y is a text. Let's say that you have a data set of query response. Let's say that you find the most similar queries in a data set, and then you want to produce the average response. Of course, this is a natural language processing task. There is no such a thing of taking the average of words. So what you have to do in the case, for example, is to produce an embedding for all of the for the sentence, look at the average of the embedding, and then produce another mapping to the word space, and so that the average is not trivially over the text itself, but it's on the features they have extracted from the text. Okay, so even if the algorithm is stated in a very simple manner, do not think that its utility is limited, because by changing by changing the number of, by changing how these distances are calculated and how this average is performed, you can have eventually a very rich behavior that adapts to a lot of different type of data. Okay, so let's finish here for now. There are many more things that we could talk about in terms of classification of cats and how this can be done in a tricky way and how to embed feature in the data. But yeah, let's stop it for now. As I said, I would like to keep the frontal part of the class kind of limited in the sense that we spend most of the time discussing the challenges and so on and so forth. So let me know if you have any question for the next 5 minutes, and then otherwise I stop the recording and then we finish the class and we start again next time. Okay? Yeah. So let me know if you have any questions.
I have a practical question. Next week, am I right that we are going to do another elevator pitch on like exercise 0?
Yeah.
Yep. And that's going to be graded, I think. Is that true?
Okay.
Is that true?
No. Challenge 0 is not graded. It's not graded.
It's not graded. Okay.
Yeah.
And also by the end of the week, we need to do something with a video or not?
Yeah, so the submission of the video will be after the final elevator pitch. So again, next week, you're going to give the final elevator pitch. You're going to do a slide presentation. Then you go home, you record yourself, you put it on YouTube, you send me the unlisted link, and you submit that on E3, I think. And then we will use this material to do an intra-team evaluation. So you will receive a form by email that says, please review the report submitted by this group. You're going to go watch the video of these 2 groups and give a ranking of these 3 groups. And then this is going to be in the Google form. So when you submit the form, we see the results and we move on from there.
Okay, thank you.
Yeah, so as I said, so the first challenge is not graded. As I said, the logistics of the class are kind of complicated, right? So because you're there, you're creating, you're submitting, you're doing the report, but this is not for us to make something complicated, right? We impose this on ourselves so that there is more value for you. So you get more value out of the structure of the class. So bear with us, no stress for challenge 0. Let's just do something fun, like it was today. So for example, if the groups, they already had a very good presentation, if they don't want to present next week, it's fine by me. Just produce the report, record the video, and that's it. And yeah, and that's it. Okay, any other question?
Can I just ask a clarifying question on what you were just talking about now?
Yeah, go ahead.
Can you tell me like exactly what you expect? But like what you expect us to do for week 1 and week 2 of the challenge that we're doing. So not just challenge 0, like for challenge 1 and challenge 2.
So the idea, I think I discussed it during the first class, but let me clarify again. So for week 1, it will be sort of mid-challenge elevator pitch. And for week 2 will be the final challenge elevator pitch. In week 1, I would like you to tell me, first of all, that everything is going well, right? So you don't have problem with the people participating or not participating. So hopefully this is going to be settled after the first couple of weeks. And then you tell me, oh, I'm stuck here. I was trying to do this. I was trying to do that. And that's more of a conversation in which you maybe ask a question and I'll give you some intuition, if I have any, on how to complete the challenge successfully. If the challenge is not written in a way that is clear, if you have some more doubts, you can ask me there. And I think that is just more of an open discussion on the type of problems you have in the challenge. And then the final challenge is going to be, the final elevator pitch is going to be more of a completed work. And you're going to tell me, oh, what you found interesting, what was something challenging for the group, what type of issues you had, and so on and so forth. Does it make sense for you? So as I said, maybe I said it and I wasn't not so clear, but like the grading that I give over these challenges, over the elevator pitch, like it's not strict in the sense that I have a certain checkpoints and from the checkpoints, I see that you guys clicked these checkpoints. So it's more that it is obvious for me how much time you spend on the challenge based on the question that you ask, right? So it is very clear from my perspective to understand how much effort you guys pour in, and usually I give a feedback on the effort that I perceive from the elevator pitch that you did. Okay, we are not here to, to be very rigid and to punish people, right? We try to reward. We use the grades to reward people that do a good job and present something interesting. Okay, that's my overall view. Okay, any other question? Sorry, hey, Luigi, did I answer your question correctly?
Yes, thank you.
Good. Any other question, guys?
How has the report has to be? Like, how does it have to look like?
I think most people would like to do is to use a Jupyter notebook, and you just provide comments on the Jupyter codebook, on the Jupyter codebook, so that you see the code that you have executed, you have a couple of plots, and you tell people why you give a certain choice, and that's it. Yeah. So I think that most people will want to watch the video first. So the slide that you make would be the one that most people watch. And then if there was something that they were not able to do in the challenge, or they wanted to do and didn't get to do, then they will want to go and look at the report to find the code and to find the explanation on the code as of why you chose to do to take a certain route in addressing the part of the challenge.
So it's the code with some comments. That's
basically from my perspective. Yeah. Some blocks and some comments. Yeah. But usually, we live in the ChatGPT era, right? So the point is that you can write down as a flow, like you can write down very quickly, just using some very informal language what you wanted to express. Then you put into ChatGPT. It gives you a nice form, which is more compact and more synthetic. You check that what comes out is reasonable. You modify as needed, and then you put in the report, right? So the report writing, in my mind, is it doesn't take that much energy out of you guys.
Okay, thank you.
Good. Any other question, guys? Okay, so if there is any other question, then I'll stop the recording.
Okay.
Is there another question?
No questions. It's pretty